Eli 5. How do architects calculate if a structure like a bridge is stable? Architects don't calculate that, engineers do. With modern engineering they can model everything in a computer simulation to get a pretty high confidence of stability. Even then things aren't engineered to be just strong enough, they have safety factors of 3 or 4 times the required strength, so even if the calculations are off there is still a lot of leeway. You have to cut a lot of corners in construction, missed some fundamental force in your simulations, or use the structure for something it completely wasn't designed for it to fail. They drive bigger and bigger trucks over the bridge until it inevitably collapses. Then they weigh the last truck and rebuild the bridge. Engineers do it. The bridge is modeled as a number of discrete elements, the stress and strain within each is calculated depending on the material being used, etc., how weight is distributed, and a million other things, and a factor of safety is applied. There's an old saying, anyone can design something to stand, but only an engineer can design it to barely stand. Usually it's the engineers more than the architects, but there are many equations regarding this. Much easier for certain types of structure, but you can break every structure down to moments and build it up from there based on material properties. That's more engineering. But from an architecture point of view you should have a rudimentary grasp of material strengths, tensile strength of building materials, and structural strengths like arches, load-bearing pillars or pylons. Computer modeling is a valuable tool. However, this isn't even necessary for the vast majority of bridges. The standards and knowledge are so well developed at this point that it's mostly a copy and paste of previous designs. The safety factors in these are huge as well. A real civil engineer would be so mad right now. Architects don't do the calculations, engineers do. That reminds me. What do architects even do? Collecting data for engineers? Design how pretty the structures must be? The architects don't do that, that's for engineers. We have a few friends called equilibrium and superposition. Structural engineering is an entire career field. The folks who know this stuff have devoted their entire careers to it. Architects use engineers to spec out all materials that have a purpose other than aesthetics. In school, has your teacher ever had you build little bridges from toothpicks and twine, and then see if a matchbox car will roll across it successfully without the bridge breaking? Professional engineers do that with really fancy computer systems. The short answer is that every material has certain physical properties that determine how well it can take certain forces such as twisting, bending, arcing, squishing without breaking or permanently deforming. Engineers account for any stress that the structure can be put under in the worst situations such as heavy wind, earthquakes, temperature changes, vandalism, wear and tear, etc., and cross-reference it with the shape of the structure and the materials used to determine if it will resist or break under those circumstances. In the very old days some architects would build scale models of structures to assess their stability. The fault of the method is that the mass of the structure would scale by the power of 3, while the thickness section depth would scale by the power of 2, so was not a foolproof method, as structures at small scale were shown to be stable but unstable at full scale. Engineer here, we learned how to do this in a class called statics. Basically the study of non-moving systems, i.e. structures like bridges and buildings. The math is surprisingly easy and it was one of my easier classes. Fluid dynamics on the other hand still gives me nightmares. You know what the structure is made of, and the properties of these materials. Like for steel you can know how much it can be compressed, bent and stretched. You can also calculate how much or little they actually change in size due to the stresses on them. Then you calculate the loads and their positions and how that impacts the structure and its individual parts. Most of it is done on computers because complex buildings have hundreds if not thousands of individual parts that need to be calculated to withstand the loads. It's easy to build a bridge that won't fall down. The hard part is building a bridge that will only just not fall down. Hi, engineering student here. I know I'm not explaining like you're 5, but, for bridges, specifically truss bridges, research truss analysis. It's the specific process used to determine the weight and strain in any one part. You can find a video about it pretty easily. Not a bridge, but we built a large storage unit recently to hold about 2,000 tons of grains, can't fit more. The structure is designed to withstand winds of about 150 kilometers height, never observed in the region, while having over 8,000 tons in storage. Needless to say, I'm more worried about other stuff than the infrastructure, which is the proper way to build stuff. The explain like I'm 5 answer is that engineers use advanced math to calculate if it will fail. Every structure has a formula that can compute whether or not it will fail based on the shape and materials. You can do this relatively easily with simple structures. To do more complex structures you either need an impossibly complex math equation, or to solve a ton of simpler math problems. So the approach is to have a computer solve a lot of simpler math equations really quickly compared to a human. Can't say for other places, but in Australia we don't calculate that as architects. We usually gain a rough understanding of structural limits through a lot of experience over the years based on what engineers approve or disapprove of. Everything we design goes through many types of engineering consultants before it ever gets a green light for construction, even for houses, whether it be an extra-story renovation or a whole rebuild. It used to take a lot of math and experience. Some things even failed because of unexpected issues. Today you can load the entire thing in a simulation with something like ANSYS Mechanical and run all the math on it. Even stuff you never knew about. You can then with confidence know within a fairly good margin of confidence everything that will happen.